You have seen that there is a relation between determinants and area or volume. In this video, you will see the consequences of that relation for linear transformations. I'll start with an example in R2. A is this matrix. We use the matrix to define a linear transformation. For a vector x in R2, T of x is matrix A times x. Here, figures of the domain and codomain of T. In the domain we have basis vectors E1 and E2. The images of the basis vectors are given by the columns of matrix A. So E1 and E2 in the domain are mapped to vectors 3, 0 and -2, 2 in the codomain. In the domain, E1 and E2 determine square PE with area 1. Their images in the codomain determine parallelogram PA. As shown in the last video, the area of PA can be calculated as the absolute value of the determinant of matrix A. The transformation increases the area by factor 6. What if we start with some other shape? For example, we can start with parallelogram PB, determined by vectors B1 and B2, the columns of matrix B. The area of the parallelogram is the absolute value of the determinant of matrix B. Here you see the images of vectors B1 and B2. And this is the image of the parallelogram. What is its area? We need the matrix with the images of B1 and B2 as columns. We can calculate the area of the parallelogram directly from its determinant. You can check that it is 13.5. However, there's a second way to calculate the area. This matrix with the images of B1 and B2 as columns can be rewritten as matrix A times matrix B. So the area of the transformed parallelogram is the absolute value of the determinant of A times B. The determinant of a product is the product of determinants. So, if we calculate further, we see that the transformed parallelogram has again an area of 13.5. It is 6 times as large as the original parallelogram. The same relation holds for any parallelogram in R2. The area of its image under a linear transformation is the area of the original parallelogram times the absolute value of the determinant of the transformation matrix. This was for a parallelogram. Does it hold for other shapes as well? Yes, it does, as long as the transformation is linear. First, we can stack squares. It is now crucial that the transformation is linear. Then the image of each square is a parallelogram. These parallelograms all have the same shape and the same area. We can approximate any shape by a number of squares. For example, this quarter circle S. The image of S is approximated by the corresponding parallelograms. The approximation becomes better when the grid is refined. Transformation T deforms the grid in the domain into a grid of parallelograms in the codomain. The transformation scales each of the areas with the same factor, the absolute value of the determinant. So the area of the whole shape S is scaled by this factor. This is the general theorem. T is a linear transformation from Rn to Rn with n by n matrix A as its matrix. S is a region in Rn. Then the volume of the image of S is the volume of S times the absolute value of the determinant of A. For n is 3, so in R3, this is the volume in the regular sense. For n is 4 or higher, so in higher dimensional spaces, this is a generalized volume. If n equals 2, so for transformation in R2, region S lies in R2. Instead of a volume of S, we talk about the area of S. Some examples in R3, so I can show nice figures. A multiplication by this matrix A makes the unit cube grow in all 3 directions by factor 2. the image of a volume is 8 times as big as the original volume. Another example. A certain matrix A has a determinant of -1/2, so the transformation halves the size of every volume. In this case, the unit cube is transformed into this parallelepiped with volume 1/2. Applying the transformation a second time transforms the parallelepiped into another one, now with volume 1/4. And once more gives a volume of 1/8. So, the determinant of the matrix gives information on how volumes increase or decrease. The other way around works as well. For some transformations, you may know how volumes change, so you can derive values for the determinant of the matrix. For example, if an object is rotated, its volume does not change. And if an object is reflected, its volume does not change either. So, then you know something about the matrix of such a transformation. Its determinant can only be 1 or -1. Another example is this matrix A. The third column of matrix A is a linear combination of the first 2 columns. The column space is not a whole R3, but just a plane. All image vectors lie in that plane. The transformation flattens the unit cube into a part of a plane. The volume of the image is 0, so the determinant of matrix A has to be 0. For a 3x3 matrix with rank 2, that is not a surprise, right? If a transformation is not invertible, the determinant of the matrix is 0. N-dimensional objects in the domain are flattened into a lower dimensional subspace in the codomain. The volume of the transformed object is then 0. Next time you see a determinant, you see more than just an indicator whether the matrix is invertible or not. You now know as well that it gives the factor by which volumes increase or decrease when you multiply all its vectors by the matrix.